So in this video, we are going to solve this problem for problem of the day on Geeks for Geeks. The name of the problem is row with max ones. It's a medium level problem. The accuracy is also pretty low. Okay. You are given a 2D binary array consisting of only ones and zeros. Each row of the array is sorted in non-decreasing order. Okay, so all the rows are sorted in ascending order. Yeah. Your task is to find and return the index of the first row that contains the maximum number of ones. Okay. So the number of rows and columns in the array are denoted by n and m respectively. Okay, n is the number of rows and m is the number of column. We need the index of the row that has the maximum number of one. We need the index. Okay. So if we are not able to find any index, then the answer should be -1. So let's say at the beginning there were no row which has any one. So yeah, let's say count of ones were -1 at the beginning. So at any point of time when we will say that okay, in this row there is this number of 1, then we will be updating the answer with that index. Makes sense. Is it going to happen at any case? Okay, so if there are no one, then we cannot update. Okay, so count should, like, answer should be updated only if there is at least one. And what if there are multiple rows with same number of 1? Then we need to return the first row. Okay. So let's see this with an example. Zeros. So because it is going to be in sorted order, so all the zeros are going to be in left and all the ones are going to be on the right. So when I will start counting from the left. Okay, so what is the brute force approach would be to go to each and every row and count the number of ones in that, and if the number of 1 is greater than our previous count, then we are going to update our index or the answer by that particular index. Let me code it up, even though it might not be the optimal solution. Yeah, okay, look like it will also pass as the container very low. Let's see, but we are going to do the optimal one as well. Let's say I'll be going to each and every row and I'll say that okay, and number of 1 in row. So which is initialized to 0, and we'll be going to each of the element in the row. And I'll be checking if this is a 1 or 0. So if array of ij is 1, and we'll update our answer by this particular index. So yeah, it is passing all the test cases. Why? Because the value of the number of, like, the value of nm, that is the number of rows and column, can be at max 10 to the power 3. So what does that mean? That basically means that if we go to each and every row and then go to each and every column, then the time complexity would be big of n cross m. Now, because n can go up to 10 to the 3 and m can go up to 10 to the 3, like as stated there, so the worst case time complexity could go around 10 to the 3 into 10 to the 3, that is 10 to the power 6, big of 10 to the power 6, which is not greater than, like, which is less than 10 to the power 8. So that's why this is going to pass. But there is one more optimal solution. So this is a follow-up. What if n and m could go up to 10 to the power 5? So instead of 10 to the 3, suppose they have mentioned it over here that, okay, in the updated one, n and m can go up to 10 to the 5, then what would you do? Then you can't go to each and every element of the 2D array. Basically, you need to find some optimal answer. And how to do that? Let's see. So yeah, take this one as example. So in that case, what we are going to do, we are going to start with the first row, and we will start iterating from the right. We will start iterating from the right, and we will check if there is a 1 or not. Yes, there is a 1, so we will maintain a pointer, and we'll update our pointer by 1 until there is a 1. So because there is a 1, we'll update our pointer. So suppose there is no 1, so pointer will stay there, and then we'll go to the next row. We'll again check if there is a 1. Okay, there is a 1. Then we'll update our pointer by 1. Like, the pointer will point to this element now. Then again we'll update our pointer. We'll say that, okay, there is no 1, so our pointer will stay there. Again we'll start from here. We'll check if there is a 1. Okay, there is no 1. Then we'll go to the next row. Here there is a 1, so our pointer will come over here. And since there are no more rows and also the pointer came at the -1 index, we'll go out of the loop, and we can say that, okay, at which point my pointer was at its leftmost point. So whenever it was at its leftmost point, or when it was last updated. Now since it got, like, it saw there is a 1, so it is not going to update itself until and unless there is a 1 left to it. So there has to be a row which has to get more number of 1 inside that, so that our pointer will be updated to a new value. Like for example, it was pointing to index number 1 uh, for row number 1, and now it will be updated to -1. Like it was pointing to row number, it was pointing to 0 at row number 1, and when it came to row number 3, then it got updated to -1. So the last time our pointer got updated, that is the index value that we need to keep, and in the end we will just return that value. So when like the pointer will start from where, the pointer will start pointing from 0, p will be 0, and when it will start to change the value of the pointer, when it will say that okay, in array of I and p there is a 1. So if there is a 1, then it will start to look for array of I and p minus 1, and so on. Like the value of p will be decrementing at each step. So p will now become p minus 1, and it will again check for the value of the array of I and p, and if that is again 1, then it will again decrement the value of p. So yeah, that's how we are going to get the index where the p is going to update at the, like whenever there is a index where p is getting updated, we need to keep the index count. That's the approach. Let's see how we are going to solve this. Yeah, and what is going to be the time and space complexity for this one? Like the space complexity was 0 for the previous approach as well, but what is going to be with the time complexity? So because at most, like we will be going to each and every row, so yeah. And what about the column? We are not going to traverse through each and every element of the row. Like we are just going to start from the rightmost, and in the worst case it might happen that we might come to the leftmost index, that is -1. So it is going to traverse at most n distance, not more than that. So it will be big of n plus m. That is going to be the time complexity. So even if n and m can go up to 10 to the power 7, then also in that case our approach will work. There will be no issue in that. Let's see how to code it up. So we need to basically keep a pointer, right? So let's say, and pointer will be pointing to the last column. What is the last column? The last column is m minus 1. We are going to go to each and every row, and we are going to start looking from the right, like start looking from the index p. That okay, if at the index I and p, like the ith row and the pth column, if there exists a 1 or not. So, and until it will exist, we are going to decrement the value of p. So if array of I and p is equal to 1, we are going to update our answer by that index, because this is the index where the value of the p is getting decremented, and also the value of p is also going to get decremented by 1. Now we are going to check this until there exists an index where there is a 1. So while this is true, we are going to check. And also there can be an edge cases. Suppose p has been assigned a value like -1, then we need to keep that as a condition that don't go beyond 0. So while p is greater than equal to 0 and array of ip equal to 1, in that case only we are going to update our answer. Yep, looks good to me. It is passing the example test case. Now let's see for the, okay, it is passing all the test cases. So yeah, that was all for this video. See you in the next one.